Good day, everybody. Justin Miller, Rockstar College Physics here. We got some lasers going on here. A little spot here, kind of hard to see probably with the lights on, but ultimately, I'll explain the system here momentarily. What we want to be looking at is a single slit diffraction now. We looked at double slit diffraction, double slit interference. I want to look at single slit interference. You may say, what? How do you get single slit interference? Well, it turns out that all the spaces in between even a single slit act as sources of spherical wavefronts, and that you get single slit interference patterns. Actually, when we had double slit interference patterns, we had double slit embedded in within single slit. It gives this really fine sort of pattern. But at any rate, let's take a look at this. Got a little wafer here with a very thin singular slit. Got a little laser pointer there. I'll turn off the lights and see if maybe you can kind of catch a glimpse of this interference pattern right here, where we've got some nice, real bright central maxima, and that's flanked by a succession of other maxima as well. So I'll take a picture of that so you can kind of see it up close. But ultimately, this is single slit interference. I'm going to get these out of the way. Turn this laser off. So ultimately, fundamentally, it works much like double slit interference did. The only difference is that we don't have two sources interfering with one another. We have a multitude of sources from within the actual single slit itself. Every point within the slit acts as a source of spherical wavefronts, and this produces all sorts of interference that ultimately produces these patterns that are observable. So, single slit. Interference is what we're looking at here. And again, like I said, it pretty much follows the same sort of correlation that we had with double slit interference. I'll just kind of cut to the chase here, if you will. And we'll note that it comes down to path length differences. And ultimately, we can do this. Minima. Occur according to A times the sine of theta is equal to m lambda, where m is equal to plus or minus 1, plus or minus 2, plus or minus 3, dot, dot, dot. No zero, because this is for minima. We don't even go ahead and have some expression that tells us where maxima are, because this is ultimately a system that's dominated by minima, very well-defined minima. All the maxima are just sandwiched in between successive minima. So generally you'll find these kind of broad interference patterns regarding single slit interference. Well, for double slit interference, it was a really, really finely spaced pattern. Comparative to that of single slit's a much more broad sort of interference pattern. So this is what we've got. Minima occur at this. Well, what is A? A is equal to the slit width. M's the order number. Theta is that angle relative to the principal axis. And of course, lambda is the wavelength of light. For single slit interference, we still need ourselves some monochromatic, coherent light in order to really see the pattern, because it is still packed in really close together, and that's pretty much the necessity there. So if we were to draw out sort of this pattern, if you will, we could go ahead, take ourselves some little thin slit there, take ourselves some principal axis, take ourselves some screen here, screen, principal axis, which is basically a line with the center of the slit and goes straight outward normal, the screen, and the slit itself. And I'm going to kind of expand this out, obviously, so we can see what's going on. We've got some light, some wavelength lambda coming in here, and shining over the slits. And what happens is, well, we get spherical wavefronts from everywhere within this slit here. And they all start overlapping spatially, and they produce the interference pattern that we see over here. So what I'm going to do is kind of draw in some spots here that represent where the maxima are, but then we'll go ahead and put in the minima as well. So, like right here, we still have the central maxima. Well, that central maxima is sandwiched in between the minima that are correlated with that expression there. So we have ultimately m equals 1 and m equals -1 minima there and minima there. Very discrete. So made it look not so discrete, but it is nice and discrete there, and that is where that central maxima is sandwiched in between. Now if we want to look at the first order max, that's going to be right there, and right there as well. And what we'll find is that first order maxima, its width, is ultimately half the width of the central maxima. We'll show how that's the case here in just a few. But that's going to be sandwiched in between m equals 1 and m equals 2 minima, and m equals -1, m equals -2 minima, there we go. And this keeps on going, where we've got another one, so on and so on, where we can start calling this like first order maxima, second order maxima, and so on and so on and so on. We just get this kind of really broad picture. Now if this happened to be double slit interference, what we end up getting is the single slit pattern, but the double slit pattern is sort of embedded within it. So we get this really fine striation all over the place in between these larger pockets. And maybe I'll put up another picture that kind of compares the two with respect to the double slit embedded or superimposed, if you will, on top of single slit interference. And that's something you can't get away from, because a single slit is, well, two double slits. Two double slits both have single slits, we should say. So you're always going to get some sort of single slit interference embedded on top of the double slit. But this is just single slit. At any rate, we've got ourselves something like this. We can go ahead and take, say this is the m equals 1 minima, m equals 2, m equals 3 min, and take this angle and say that this is theta 3. Well, we have to put theta 3 sub d because we don't need it to be dark. There is only minima. If you want to put on a d in there, that's fine too. But ultimately, we've got the slit width. A, we've got a theta, we've got an m, and we've got a lambda. And we've got that a sine of theta equals m times lambda for the minima. Maxima, again, just sandwiched in between successive minima. So, very similar, once again, to what we had with double slit. Same sort of expression there. Just got to be aware of, are you talking about double slit, are you talking about single slit, are you talking about both? What are you looking for? Minima? Are you looking for maxima and minima? But ultimately, that's kind of what we've got going on. We can start talking also about locations that the minima occur, or the spatial extent of maxima, because now we can start to say, well, what is this width of the central maxima, right? Well, the width of the central maxima would be this distance right there. How do we start to figure that out? Well, we've got like a y1 and a y-1 regarding the locations at which the minima occur on the screen. We have a screen distance L, much like we did with the double slit case, and we've got that y in general is equal to L times the tangent of theta. So I'll also go ahead and put that down because we already know that y is equal to L times the tangent of theta. And then if we really wanted what that width was, well, we could take those two quantities as positive and add them together, or we could take y1 minus negative y1, if that turns out to be a negative quantity, and there we go. So what we'll do is we'll look at a little problem involving some single slit interference, quantify some stuff out so kind of see how it works out, and I'll pretty much be that because of its familiarity. So let's take a look at the problem. Be right back. All right, so here we go. We're going to take ourselves. Nice problem. Here it is. Okay, so what do we have? We got some light with a wavelength of 650 nanometers. We've got a single thin slit that has a slit width of 0.75 millimeters. We've got a screen that's located at a distance of 1.50 meters away, and we're asked some questions like, hey, what's the angular width of the central maxima? What's the linear width of the central maxima? What's the linear width of the first order and second order maxima? I just want to make some correlations here with those widths, and that's pretty much that. So, I guess we could draw this out. Yeah, why not? Draw out a little mini of it. So we've got this going on. We've got this, and we'll go ahead and put our screen here. So we're going to go ahead. I'm going to use red because I should. So we're going to go ahead and take this, and then we're going to take this. We're going to take this. So there is the central maxima, first order maxima, second order maxima. Everything ends up being symmetric about the central maxima, yeah, or the principal axis. Likewise, we'd have first order and second order there too. But nonetheless, this is what we've got. We want to know what is both the angular and linear width. Say central maxima width. Central max. And then we've got that. We've got that. First and second order maxima widths. And what do we have? Well, everything goes with M values that correlate with the this one. They correlate with the minima, right? So this is the M equals 1, M equals 2, M equals 3 for the minima. Here's the M equals negative 1. And what we can do with all of this, start to put things together and figure out what we need to do here. So the first question is, what is the angular width of the central maxima? So I'm trying to make this not too messy, but go like this. And we ultimately want to know what is this angle. Let's just call it some angle delta. So with that angle delta, we've got ourselves this angle, which we have being theta 1, and we've also got this angle, theta negative 1. So let's just go ahead and start putting this stuff together, quantifying this out, and moving on from there, shall we? All right, let's do that. So, A, we want to know what delta is. Well, let's go ahead and figure out what theta 1 and theta negative 1 are, and we can just kind of put them together and figure out what that total angular width is. And we'll extract out some other meaningful information pertaining to that. So we've got ourselves A times the sine of theta 1 is equal to 1 times lambda, because ultimately we're going A sine theta is equal to m lambda, as we've just discussed. So this is what we've got for this theta 1 here, and it's equal to 1. We've got lambda there, and we've got that theta 1 is then equal to arc sine of lambda over A. Again, what you got to be careful of is just putting numbers in. Lambda is 650 nanometers, and A is 0.75 millimeters. So we want to make sure that we're putting those quantities in properly. So we've got the arc sine of, I'll just go ahead and say 650 times 10 to the negative 9 divided by 0.75 times 10 to the negative 3. Then there's no mistaking anything. And we can go ahead and get our subsequent angle in degrees. Let me make sure we're in degrees here. Yes, we are. And arc sine 650 negative 9 divided by 0.75 gives us 0.04965. 0.04965 degrees. And that's what we've got. So there is theta 1. Well, what about theta negative 1? Well, theta negative 1 is going to be equal to the arc sine of, well, now m is equal to negative 1. So we've got the arc sine of negative 1 multiplied by the angle, divided by the wavelength, 650 times 10 to the negative 9 meters. Put this here, n is equal to negative 1, divided by 0.75 times 10 to the negative 3 meters. Oh, what's the difference between these two? Just a negative sign, right? The sign of a negative number is the negative sign of the number, so ultimately we're just going to get ourselves negative 0.04965 degrees. So in this particular case, we can either just add up the absolute value of the two, or we can note that this is going to be 2 times the width from the from the principal axis to the m equals 1. It's symmetric, is the point here. So noting that theta 1 is equal to negative theta negative 1, we'll have that delta is equal to 2 times theta 1, which is then going to just be equal to 2 times 2, gives us 0.9931. Almost 1 degree. There is the angular width of that central maxima. Fantastic. That's what we're asked for. That's what we get. All right. So now we move on and we say, well, what about the linear width? What is the spatial extent of this maxima? Well, that's going to depend on how far away the screen is, right? The closer the screen is, the smaller the distance in between, well, theta 1 and theta negative 1. That's preserved though. The angular width is the angular width no matter what. The linear width depends. So we've got this distance L here, right in here, L right there. And ultimately, we can go ahead and figure out what the distance is from the principal axis to the m equals 1. I'm going like this. There is m equals 1, and this is alignment of the principal axis. This would be half of the angular width, right? This is our theta 1 right there. Well, we also have something down here like this that goes like this. Yeah, that's not drawing out so symmetrically. Like this, where this would be m is equal to negative 1. Here would be our theta negative 1. But we already know that there's symmetry in between these two thetas, so there has to be symmetry in between these. So let us just find this distance right here. we'll call this distance a y1. Well, this distance would be y-1, and that total distance here, even though deceptively drawn, should just be 2 times y1. The angles are the same, then the linear separations have to be the same. At any rate, we've got, in general, that y is equal to L times the tangent of theta. Thus, y1 is equal to L times the tangent of a theta1, which is then equal to 1.5 meters times the tangent of 0.4965 degrees, which gives us tangent 0.4965 gives us 0.00130. 0.00130 meters, or about 1.3 millimeters. That's great. Well, what's going to happen when we go ahead and say that that's negative angle? We'll get y-1 is going to be equal to negative 0.00130 meters, which is going to ultimately give us that this width of the central maxima so I'll just call something delta y central maxima is going to be y1 minus y-1. Take the difference between them because this one's negative, and we're just going to get 2 times that, which is going to be equal to 2.60 millimeters. There we go. There's the width of the central maxima. Fantastic. Linear width. So let us look at the linear width of the first order and the second order maxima, and then that's pretty much that. If you can do all that stuff, you are golden. I'll do width of first order max. Well, the first order maxima is sandwiched in between the second order and first order minima. So we need to figure out like a y2 minus a y1. So we will have that this width, we'll say delta y first is going to be equal to y2 minus y1, where these are the linear distances at which the second order minima and the first order minima occur at, relative to the principal axis. So if I take this total distance and I subtract off that, I've got that distance in between them. That's exactly what we want. So what do we know with this? Well, y2 is going to be equal to L times the tangent of theta 2, and y1 is equal to L times the tangent of theta 1. We already know what theta 1 is. That's the 0.04965 degrees from before. I have erased that, but oh no, it's up there. And then we've also got ourselves the necessity to get what theta 2 is. So let's get theta 2. Theta 2 is going to be gotten by taking a times the sine of theta 2 is n lambda, where n now is going to be equal to 2. So we've got that theta 2 is going to be the arc sine of 2 times lambda. So we've got 2 times 650 times 10 to the negative 9 divided by the slit width of 0.75 times 10 to the negative 3. Meters cancels out, not worried about that. And what do we get out of this? We've got ourselves the arc sine 2 times 650 divided by 0.75 e to the negative 6. Excuse me, negative 3. I get 0.09931. That number seems a little familiar. 0.09931. I've erased it, but you go back and look at some of the numbers that we had. Oh yeah, that number. That's weird. That was kind of like the angular width. No. Said that before. That's okay. Never mind. We've got this. I put that was almost a degree. before when I was doing the angular width central maxima, I forgot a 0. It wasn't 0.9931, it was 0.9931. Oops. All right, moving on though. We still got good numeric values. We went back, that's all right. The angular width of the central maxima, I forgot a decimal place. So, okay. I move on, you move on too. So here we go. We've got theta 2 is equal to that, and we know that theta 1 is equal to 0.04965. Thus, we've got the width of the first order maxima is going to be equal to 1.5 meters multiplied by the quantity of the tangent of 0.09931 degrees minus the tangent of 0.04965 degrees. Boom, 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 boom. And I already know what it's going to be. It's going to be 0.0013 meters or 1.3 millimeters. But let's still calculate it out. I got 1.5 times the quantity of the tangent of 0.09931 minus tangent of 0.4965. Oh my gosh, that's what I get. 0.00130. So we've got ourselves 1.30 millimeters. So what's that saying? Well, that's saying that the width of this first order maxima is exactly 1/2 the width of the central maxima, which is equivalent to the distance from the principal axis to the m equals 1 minima. So that distance there is equal to that distance there, and we're going to find that it's equal to that distance there. There's this preservation, everything's packed in, you got small angles, so sine behaves in sort of a linear way here, and that's how this all ends up playing out. So let's just get, for the second order maximum, really quick, the linear width of it, and that will be that. So now I want delta y second, that's going to be equal to, now we're looking at this portion right here. We've got a y3 and a y2. The difference between y3 and y2 are going to be what the width of that second order max is. So we've got a y3 minus the y2, which will be equal to L times the tangent of theta 3 minus L times the tangent of theta 2. We already know what theta 2 is. We just need to get what theta 3 is. Theta 3 is going to be equal to the arc sine of m lambda over a, where m is going to be equal to 3 now. So we got 3 lambda over a. We know what lambda is. We'll compute this out. And we got ourselves the arc sine, 3 times 650, 955.75, negative 3. And I get 0.14897, 0.14897 degrees. Excuse me. Ooh, need some water. All right, so there is our theta 3. We know what theta 2 is, the 0.09931. And from there, what do? Let's go ahead and stick it in here. This is going to be equal to 1.5 meters multiplied by the difference of the tangent of 0.14897 degrees minus the tangent of 0.09931 degrees. And, oh, what's that going to end up being? That's right, 1.3 millimeters again. Let's just go ahead and put it in though for the satisfaction. Tangent of 0.14897 minus tangent of 0.931. And oh my gosh, I get 1.30 millimeters. 1.30 millimeters. So do note, once again, that in part A, where we're looking at the angular width, I skipped out that 0 there. I just put 0.9931, so it was almost a degree. It's almost a tenth of a degree, not almost a degree. Should have caught that, my bad. Catching it now. At any rate, what we've got here is a high degree of symmetry, and we've got, hey, the linear width of this is twice the linear width of the successive maxima. So with this, I'll have a nice little picture that kind of shows the succession, and yeah, we'll throw in the picture, we'll throw in the picture of the double slit too, and can kind of compare the two. See how the double slit's embedded within the single slit diffraction pattern. And that's pretty much that. All right? So I'll say goodbye for now, but I'm going to put up a picture. So don't go. All right? Bye for now.